You can have the sheets that I provided. Those have the trig sub on them, right? They have what you do with the different powers of, sine, cosine, trig integrals. I think it's sufficient. Yeah, sorry. Well, 48 hours, we'll be taking a test. You'll be taking a test, yes? So I thought I'd start class with just a few problems. I wanted to maybe talk a little bit about problems that would be on the test sort of thing, but then I was ready to move into the next section, even though it's not on the test. Because we don't have time for just complete review days in here. It's just too much stuff to cover. So, all right, so let's throw this up here and see what happens. I don't have my computer today, so we're just going to do it this way. All right, so when you're looking at this problem, you should be thinking right away. There should be very little hesitation in terms of knowing that this is an improper integral. And that's because the limit of integration is infinite, right? So you know it's either going to be the type 1 or the type 2. What's the difference between the two?
Type 2 has a discontinuity, I think.
Yeah. So the type 2, which is what we did last class, is where we have problems within the integrand where it's undefined. So in this case, we would be undefined at 0, right? But 0 is not in our interval, so we're not worried about that. However, we have an infinity on a limit of integration, which is the type 1. So this is an infinite interval as opposed to an infinite integrand, type 1, right? So how do we handle type 1? Yeah, we're going to turn this into a limit. So we're going to say this is equal to a limit as what approaches what? T goes to infinity of the integral from 1 to t, and then just rewrite, right? Like that. All right, now we've got that set up. Now we need to actually find the antiderivative. Yes? Integration by parts, okay. So, wow, this is actually going to require that? I don't think we had a problem like that last class, did we? So, you did in the homework, yeah. You did in the homework. So I'm going to set this problem up as an indefinite integral over here first, just to go find the antiderivative. So you said integration by parts. If I do integration by parts, that means I have to choose a u and a dv. And so what would you choose for u?
U would be ln
x, x to the negative 4 dx, right? Because we're going to rewrite this x to the 4th in the numerator as x to the negative 4th. Be real careful. I know that's not what you meant to say, x to the 4th, but that's one of the most common mistakes I see on a problem like this. Even if students are doing the integration by parts, which is correct, they'll do that. And that's not right, because you don't have x to the 4th, you have 1 over x to the 4th. So make sure you write that negative 4 there. And the reason why you're choosing this is for u is because the derivative of it's going to give you a power of x, 1 over x. And then when you integrate this, you're going to have a power of x. And then when you do your voodoo, it's going to be powers of x, so it should be nice. So du is 1 over x dx. And the antiderivative of this should be negative 1/3 u to the negative 3. Not u. I don't know why I put u. X. I'm still in the weekend there. All right. So now we have ultraviolet minus voodoo. So this integral becomes ultraviolet, these two multiplied, which I'll write as negative 1/3 natural log x. Yeah, you know what? I'm going to put the... I don't know how I want to do this. I guess I'll put the natural log x on top, and I'll put the x cubed on the bottom. Okay, that's this times this. Agreed? All right, now we have minus the integral of voodoo, which is the diagonal. And I have a negative 1/3 inside, which I can pull out, and that'll make it a plus 1/3. And then we have still in here what? So when I multiply this times this, yeah, so it's really just going to become 1 over x to the 4th. This is 1 over x cubed. It's 1 over x. You multiply those together, you get 1 over x to the 4th. So I get x to negative 4 dx in there. Just going to leave it as a power because I'm about to integrate it. No more natural logs though. Yes? I'm doing this separate. Okay, so this is like scratch work on the side because I need to know what the antiderivative of this is, right? So I'm going to figure that out over here. And then when I'm done, I'm going to come back.
Just like put the limit and whatever you got in parentheses.
That's right. Yep. Okay, so one more thing to do here. Take the antiderivative of this, which we already did, right? We already know that that's that. So I'm going to get another negative 1/3 to come out, right? So I get another, I can't say that. Forget it.
Another negative.
Yeah, thank you.
Anything to help.
All right, thank you. Okay, so antiderivative of this is this, and then I hit it with this, and we should be here. So that's our indefinite integral. That's the piece that we want to be able to plug in right there. Don't need the plus c because it's going to be subtracted and added, so it goes away. All right, so back to this. Equals limit t goes to infinity of the antiderivative, which is negative 1/3 natural log x over x cubed minus, I'm going to rewrite that last one as 1 over 9x cubed. Yeah, and then what comes after that? That thing, that bar thing, we call that the evaluation bar. So this is going to be 1 to t. And you know what? You can put this in parentheses. It just kind of looks better if you put the whole thing in parentheses, I think, don't you?
A question for you.
Yes.
If we, for whatever reason, neglect to do that notation but still get the problem right, are you going to care?
If I do what? If you do what?
If we neglect to do the whole straight bar t to the 1, or 1 to t,
So what are you going to do instead?
like instead of setting it up like that, just put it in the brackets and move and go on your merry way. Like solve it, like
So
set it
you're
up
gonna-
in the brackets and solve. the
You mean
problem.
like put the t in there and put the 1 in there
Yeah.
without writing this step?
Yeah.
I'm not going to take off, but I would say proceed with caution with
Sure.
that because you can lose track of things pretty easily. And down the road, like, I don't know, you need Cal 3 or no?
No,
Okay,
but I do
so.
need physics and I do need.
So if you ever have functions of more than one variable, then when you're plugging, like right now we're plugging 1 in for x, right, and 1 in for t. That's because the only variable in the problem is x. But if you have multiple variables in here, then you could be plugging this in for either x or for y. And so you have to keep track of it.
Like implicit.
And so if you start doing all that in your head, it starts to get really messy.
I see.
So, okay, shall we continue? No limit yet, right? No limit. We're just going to hang out here with this. Okay, I should have warned y'all before class started. Whoa. Hold on. I apologize. My daughter was in a car accident on Thursday. So she's okay, but she's at the doctor right now, and I meant to silence my phone. Okay. All right. So first goes t, right? So I like to do, I'm going to do a bracket because of the limit, and I'm going to have something in here minus something in here, like that. That's what I'm going to do. So t goes in first, which really you're just rewriting everything. Negative 1/3 natural log t over t cubed minus 1 over 9t cubed. And then when we plug 1 in, let's see what we get. Negative 1/3 natural log of 1, 0. 0 over 1, right? 0 over 1 is 0, okay? And then when we plug in 1 here, we get minus 1/9. So this is going to go away. but we do have a minus 1/9 in there. What's our next step? What's that? Yeah, let's let t go to infinity now, right? So we take a limit now. As t goes to infinity, what is natural log of t approach as t goes to infinity? So you're visualizing the natural log function. As you go to infinity, it's going like that, and it's growing slowly, going to infinity. The denominator is also going to infinity. Infinity over infinity, we're going to need L'Hopital's rule, right? Over here, we have 1 over something that's getting infinitely large, right? So 1 over something that becomes infinitely large squashes down to nothing, so that's going to go to 0. So we know this limit's going to 0, and we know this limit we have to figure out, right? Question mark on that. So I'm going to do some scratch work again on the side. I'm just going to ask myself real quick, what is the limit as t goes to infinity of natural log t over t cubed? I don't even care about the negative 1/3. I don't even care about that. That's not the part that's problem, right? I just care about this piece. So we have infinity over infinity. So we use L'Hopital's rule. I think I told you all I use an L, not an H, but most books put an H and they circle it. I do an L. So L'Hopital's rule says if you have infinity over infinity, or if you have what over what? 0 over 0. Those are the two things you need to use L'Hopital. So we have infinity over infinity, so then you take derivative of the top and bottom separately. Derivative of the top here is 1 over t. Derivative of the bottom is 3t squared, right?
9t squared? Oh. Oh, we just did the L.
Do what?
You couldn't keep the 1/3 with it and make it 9t squared?
Oh, I could, yeah. No, but I said I'm ignoring that. I said I don't even care about that number. I just want to know what happens to that, right?
Okay.
Then I'll tack the negative 1/3 on if it turns out to be a nice number. So this is, I'm going to write that as a fraction over a fraction, like this. So it flips. And so this should be limit t goes to infinity of 1 over 3t cubed, right, when you flip that up. And I know that limit goes to 0, right? You have a fixed number on top, bottom becomes infinitely large, that goes to 0. Okay. So now we know what this does. This goes to 0, so now that negative 1/3 really doesn't matter anymore, right? So we know this goes to 0. So that goes to 0, that goes to 0, and this was minus 0 minus 1/9, so the answer is 1/9. That's it, yeah, this is 1/9. Questions? Nice little problem there, huh? Let's do another one. I'm pulling these problems out of the book, but I'm pulling them out of the chapter review, which is always, if you've done all your homework and you want some more practice, it's always good to go to the chapter review because they don't prompt you as much as to what technique to use, and especially for chapter 6. You have all those different techniques of integration in here, right? So these problems in chapter review, they ask you to find the antiderivative, and it could be integration by parts, partial fractions. So that's a good study guide, I think. Definite integral, right? Definite integral, because of the limits of integration. We have a problem at 2. We have a problem at 2. At 2, this is undefined. Also, we have problems anytime this radicand would be negative, right? Anything under this root, if it's ever negative, we have an issue. But the only time this would be a negative number is if this number here was 2, well, it would be at 2 we have a problem, but if we're, which side of 2? Left side, like if we're at 1 or 0 or something, these would all be negative numbers, right? So, but that's okay because our interval is going from where? 2 to 6. So we have a problem at 2, but we don't have any other problems from 2 all the way to 6. So since we have a problem at 2, this is a type 2 improper integral. Are y'all sick? All I hear is coughing and... Okay, I know, I have some allergy. Oh, it's you? Do you have a cold? No, I don't know where it was coming from. It sounded like it was coming from everywhere, so I'm like, no. Okay. No, you don't have a fever, do you? Okay. I'm going to send you home, give you a doctor's note and send you home. Send you to the nurse. Okay, so we have a problem. We have a problem at 2, right? So what we're going to need to do is we're going to need to approach 2 from the right-hand side. Why are we coming from the right and not the left?
Because it can't be a negative number.
Yes.
And it's between 2 and
Yeah, we're going from 2 to 6, so we're not even looking to the left of 2 anyway, right? So I'm going to rewrite this. I'm going to say this is equal to the limit. I'm going to use t again. T is going to approach 2 from the right, so I put the plus sign on it. And then we go integral from where to where? T to 6. Do you think I care if you put 2 plus? Or like if you left off that plus, do you think that I'm going to care? Yeah. Yes, I'm going to care. Because it won't be, it's incorrect. You can't take the limit from both sides because it's undefined from the other side. You can't. So you must state that. All right. And now at this point, we just need the antiderivative, right? So again, I'm going to come to the side here. I'm going to do the integral x over root x minus 2 dx. Okay, how many of you know how to do this integral right now? Just raise your hand if you know. No? Okay, I'm just... Because I was going to call on somebody. Let's call on someone. This will be fun. Erica. Okay, so nobody help Erica. No helping Erica. Okay, so imagine for a moment you're Erica. You're sitting there, you're taking this test, right? You've got 45 minutes left. Right, here you go, you got this problem. Okay, any ideas as just, I mean, you've got to try something, right?
I guess I would try U sub.
Okay, what U sub would you make? Okay, so you got to try something.
X minus 2.
Okay. Is that your thought or no? Tell me the truth.
It's probably what I would go for, but I didn't hear
Okay.
it.
Okay. So I don't care if you do. I just want to, that is going to work. Okay. But that sort of like, I'm going to try this. I don't know how to make people see that. It's the experience of doing enough of these. So let's talk about why we didn't do other things first. Why am I not going to use trigonometric substitution? There's no squared minus squared. Now I see the root, which makes me all excited, right? But then I don't have squared squared, so can't use trig sub. What else? Partial fractions? Nah, this is an irrational expression. So what else we have? Trig integrals like sine and cosine, tangent, secant? Nope. And what else is there? Integration by parts? Maybe. Maybe, but I'm trying to figure out what would my u be and what would my dv be. Basic u sub, let's go for it. Let's see what happens here. U is equal to x minus 2. Du is dx, right? So I'll be able to rewrite the integral. The denominator becomes square root of u, doesn't it? Root u. The dx becomes du. The only thing I need to figure out is what the x is. But I can go back up here and replace it with u plus 2, right? And why is that a good approach? What can I do now? Split it. Yeah, now you can split it. You can do u over this, 2 over this, right? Because you have a single term, 2 terms. So what is u over root u? Root u. That sounds vulgar, doesn't it? Root u. Okay, and then 2 over root u. I don't even like that. U to the half plus 2u to the negative half. du. So that over that's u to the half. That over that's 2u to the negative half. Writing them that way because we're about to use the power rule. So I guess I need a little more room. Antiderivative of this is going to be 2/3 u to the 3 halves, right? And then the antiderivative of this one should be 4u to the half. Not negative. U to the half plus c, right? And now replace u with x minus 2. So 2/3 x minus 2 to the 3 halves plus 4 times x minus 2 to the 1/2 plus c. There it is. That's our antiderivative right there. Yeah? And that's now going to get plugged in. We got to do a limit on it. So this should be equal to, let me bring it up here so y'all can see it better. This is going to be the limit as t approaches 2 from the right-hand side of the antiderivative, which is 2/3 x minus 2 to the 3 halves plus 4 times x minus 2 to the 1/2. And then I want to evaluate that from t to 6. Yeah, doesn't matter. Make sense? All right, let's plug in 6, let's plug in t, and then we'll take a limit. Limit t goes to 2 from the right. Okay, we're going to have two things here. When 6 goes in, we'll just have 6 minus 2, right, which is 4. So 2/3 4 to the 3 halves plus 4 times, again, 6 in here, we get 4 to the 1/2. And then we plug in t. I realize this is tedious to have to write this all down, but questions? All right, let's do our limit first before we figure out what's happening up front, because if this limit, remember, if this comes out to be like infinity or something, then this thing we'll say would diverge, right? So if t goes to 2 from the right, remember that means we're a little bit bigger than 2 as we're approaching 2. So if I plug that in here, this is going to approach 0, isn't it? And 0 raised to the 3 halves should still be 0. And then this right here will approach 0. And then to the 1/2 should still be 0. Do you all understand why it's so important that we're coming in from the right, though? Approaching 2 from the right. These little numbers that we're getting closer to, like 2.000001, whatever it is, we're approaching to. When I plug that in here, this is a positive little tiny number, and you can take the square root of a positive number. If you came in from the other side and put it right here, you would have a little tiny negative number, and you can't take the square root of a negative number. So that's why the side that you're coming in from is important. Doesn't change the answer. We still get 0 here, right? We still get 0 here. So would you all agree this whole thing is gone? Okay? Yes? This t minus 2 is approaching 0 as we let t go to 2, right? If you let t go to 2, but through positive numbers. Only because we're approaching 2 from the right. Right? Take that number, 2.000001, plug it in right there, subtract 2, you'll get a tiny little positive number, which you can take the square root of. All right, so that's gone. Yes?
I know that the whole notation with limits and understanding what it's actually doing is important. In this particular problem, wouldn't it have also been possible just to do bracket plug in 6 on the left and bracket plug in 2 on the right and still end up with the same answer?
You would on this problem, yes.
Particular one.
This particular one.
Unless it was like infinity over negative infinity.
Yeah.
Or from negative infinity to infinity or something.
Like on the last answer, on the last problem, did we get an answer, a nice number?
Yes.
Okay. You would not have gotten 1/9 had you not done that. Had you just plugged in the 2 endpoints,
Yeah.
you would have not gotten 1/9. You had to do that L'Hopital's rule part to get the 1/9.
I see.
This one, it just works out that you don't need, the limit's so nice and clean, it just goes 0, 0, that there's no issues.
Sure.
And you kind of get lucky if you, well, on the test, if you just plugged in 2 endpoints and got the right answer, you wouldn't get much credit for it. Yeah, because you would have gotten lucky as opposed to doing the right technique. Okay, so here, this means the square root of 4 cubed, right? So that's 8. So we get 16/3. That's this, and then plus, let's see, square root of 4 is 2, 8 plus 8. Common denominator. 40 thirds. 40 thirds. It's converging, right? Remember when it came to these improper integrals, we either had convergence or divergence, right? When we get a nice number, right, that's when we get convergence. When do we get divergence? Okay. Let me ask again. With improper integrals, you either have convergence or divergence, right? You have convergence when you get an answer that is a number, right? You have divergence when it does not exist, infinity, when it's not a number, okay? That's when you have divergence. It's easiest to remember it that way. Convergence is when you get a number. 1/9, right? We got that in the previous problem. Converges. 40 over 3 converges. Anything else that you get as an answer, either your limit doesn't exist or it goes to infinity or something crazy, right? Then it's divergent. All right. I like those. Let's in some fashion, this is kind of like a review. I mean, we've done integration by parts, right? We had a basic U sub right there. There's a whole lot of stuff we haven't had, though, right? A whole lot of stuff we haven't had. Partial fractions, all that. Yeah. Oh, wait, that should be arc sine, not arc tangent. No definite integral. So I guess we're just kind of having an open session here of just doing some problems together, all right? This is quite interesting. So I'm looking at this right now and I'm just like, I don't know if we've seen anything like that before. What do y'all think?
Seems to me like we could do where you set x equal to something and then the square root equal to something. Because you could technically, you need to find the opposite of it, so you could use a regular triangle.
I'm not following.
Maybe not.
What? What about chain rule?
Does that just make it harder?
I don't know what you mean by chain rule.
Like taking
Power rule? Power rule? Not sure.
Like one
Still
half,
not following
like
you.
1/2 inverse sine x. Like that, like instead of it being like the derivative power rule would be like 1/2 inverse sine x plus c. Considering the whole thing is
Yeah, but
is squared.
if you take derivative of that, you're not going to get that. That would be too easy.
Well, sometimes it's simpler sense or something.
That's true. That's true. All right, so what do y'all want to do? I mean, should we erase it and just move on? Yes. You want to try parts? I think that's probably the most reasonable thing here. I don't see a basic u substitution. Like, if we do a u substitution, we're supposed to see something in its derivative. If we choose u as basic u sub, that's probably the best u I could choose, arc sine of x, and derivative of that's like 1 over square root of something, blah, 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 right? I don't see that anywhere. So integration by parts, let's try it. If we do integration by parts, we've got to choose a u, and we've got to choose a dv. So had you already come up with what you want to try for u? What did you want to do the whole thing, or did you split it? The whole thing. Okay, and that means that dv has to be dx. I'm cautiously optimistic. Okay, so let's see. du, we have to take derivative of this. So derivative chain rule, right? 2 comes out. 2 arc sines of x, then times 1 over the square root of 1 minus x squared, right? That's derivative of arc sine. Yeah. And then dx. Does everyone understand what we're doing? Now we go here up. V is just x. What do y'all think about this? Do y'all like this? Have any? Is it still going? Should we still go? It cleans up? Okay, so let's just write what the formula says. It'll be ultraviolet. So that's x arc sine of x squared. Right? So that's ultraviolet, these two multiplied, minus the integral of v du, right? V du, which is going to be this times this. I'll pull the 2 out. And I guess I'm going to write arc sine of x times x over square root of 1 minus x squared dx. Is that where we're at? No. This x over that, and then this arc sine I put here, and the 2 came out. Okay, I guess we're following your lead over there. Yes. So what now?
We got integration by parts
Again? You want to integrate this again by parts?
Get rid of the x.
I think if you do use up,
Yeah.
looks nicer. Okay, do use up first.
You want to do a u sub? What do you want your u sub to be?
So if I let u be sine inverse of x, then it would become u sine u du, which I think is something we've seen before. Because du is 1 over the radical.
Yeah.
U is sine x, and then x becomes sine u.
I'm just trying to think of what
So you have
would make the most sense for most students in here. Here's what's being suggested. I like this idea a lot, to make this substitution. Okay, we could go to integration by parts right now. We would do this is u again, and this is dv, and we'd have to integrate that. Integrating this would be a basic u sub, because you could do 1 minus x squared is your u. Integrate up, you could get that, because that's like du. So that should be integrable. Then the derivative of that we should be able to get. But making this substitution, u is equal to arc sine of x, basic u sub. Du would be derivative of this, which is 1 over square root of 1 minus x squared dx, right? Agree? Okay, so now if this is our basic u sub, I can replace this with what? This with? U, right? I can replace the 1 over square root with du, but then what would I need to replace the x with? That's the critical part. What do you replace x with?
You could sine x.
Sine of u equals x if you take sine of both sides of this. Yeah. So let's rewrite that. Get rid of this. Okay, so this becomes equal to x arc sine of x squared minus 2 times the integral, and we've done all of this substitution, right? In here. So it's going to be u, that's going to be sine u, and all of that's du. So it's just u sine u, du. But that's still going to require integration by parts now, right? Okay. Yeah, it's a little nicer to look at. Okay. Do we keep going, or do we feel like we have it now? Like we could get it from here? What do y'all want to do? You want to keep going? Okay. So let's finish this up. So now we're here. We just have to remember what u is, everyone. Remember what u is. U is, we made a substitution. U is sine inverse of x, right? Okay, so now we have to do integration by parts again on this.
We use w.
We'll use w here, and I'll use dv here. So what is our w going to be? U. dw, so this is u, this is du. dv has to be sine u du, and v has to be negative cosine u. Now remember, this problem came right out of the book, chapter review. So I mean, this isn't like me trying to pull like the hardest problem I could. This is a problem in the book. So this now becomes x arc sine of x squared minus 2 times, now I have another integration by parts here, which will be ultraviolet, which would be negative u cosine u, minus the integral of voodoo, which is going to be cosine u du. I have that negative again, though, right here,
Plus.
voodoo, so it's going to make that integral a plus. And then I can close that out. And we know the antiderivative cosine. So this is going to be x arc sine of x squared minus 2 minus u cosine u plus sine u plus c.
Did you do anything with cosine of arc sine of x?
Cosine of sine, where?
So you have cosine u. If u is arc sine of x, you have cosine arc sine of x, right? Did you do anything with that?
You could probably rewrite that as an algebraic expression.
Because it was like sine, it would
Just be x.
right? That's the next term.
Yeah,
So
we.
cosine squared, you can make it like sine squared and then have sine of sine.
Yeah, let's plug it in first, and we'll take a look at it. Remembering now, everyone remember, u is arc sine of x. Correct me if I'm wrong. U is arc sine of x. So we know that sine of u is going to be x, right? Just so we have this. We want to get everything back to where it belongs. So everything back to x. Arc sine of x squared. I'm going to go ahead and distribute that through. So I get plus 2. U is arc sine of x. And then I have cosine of u. What's cosine of u?
Cosine inverse sine x.
It's cosine of sine inverse of x, right? That's what this is going to be. Cosine of arc sine of x plus sine of u, which is sine of arc sine of x. Yeah, the -2 needs to go through there. Thank you. -2, and then that should be it, right? Plus c. I'm going to, yeah, I mean, I'm going to. Yeah, I mean, I could have just used that. Yeah, I was just looking up here, sine of arc sine, it's going to go away. Okay, so I have one more line, I think, before we have a final answer.
Don't the sine and inverse sine cancel each other out?
That's what we were just saying. Yeah, that's what we were just saying. Okay, so we should be here. We should have this in the beginning. Then we should have plus 2 arc sines of x times cosine of arc sine of x minus 2x plus c. I think I got everything copied down there, right? Wow, that was messy. That's messy. So what was also being suggested is there something that we could do to replace this piece with something? Like, is there another expression we could have there? So I think we might be able to. I mean, this is fine. We're done. But let's just call this piece in here. Let's just call that, what's the letter we haven't used? Y. Let's call that y. Then we really want to know what cosine of y is, right? We want to know what cosine of y is. But to say that y is equal to arc sine of x means that sine of y equals x, just taking sine on both sides. And that means if I draw a reference triangle, my angle is y, sine is the opposite over hypotenuse, then that means this side is 1 minus that, right? So now we want to know what cosine of y is. So what's cosine of y? It's the square root of this over 1. So I could replace this whole expression with square root of 1 minus x squared. That make sense? That, I thought that's what you were suggesting we could, yeah, so we could do that. Wow. That's kind of a very messy problem. I mean, not like crazy, but it's definitely seems a little out of place. I'm wondering if there's an easier way.
Oh.
No, I'm just wondering if there was.
Oh, okay. If you're about to say you spent 15
No, I'm not saying that. I'm saying the only thing you could have maybe done is in the beginning done this. You know, like that. Right? Like maybe you could do that. This is just a thought here. Then do integration by parts. Okay, so let u be arc sine of x. dv has to then be what? Arc sine of x dx, right? And then when you take derivative here, you get 1 over square root of 1 minus x squared dx. And when you integrate this, well, that would require its own integration by parts. So you would have to come over here and do integration by parts on this, which I believe we did this once, or something similar to this. Actually, wasn't this on the test?
Yeah, we did a cosine.
Maybe it was cosine inverse on the test. So this is doable with integration by parts again. And then that would be your answer here, and then this voodoo would probably be doable. But it doesn't save it. I don't think it saves us any work that way. Okay? Yeah. God, look at that. I'm going to erase that. So maybe it's worth a quick check. Do we want to check our answer? No, we don't want to check that answer. Take the derivative. I think on the test that problem would be a little bit out of bounds in terms of what I'd want to ask. That'd be more like a bonus question. But, you know, like I said, having the chapter review here and just doing problems is a good practice because you don't know what to expect, right?
You could split that up and do integration by parts. U is tangent inverse tangent x, and then dv is 1 over 1 plus x squared, which is then inverse tangent for v.
You could do that, but I do think that's probably longer and harder than you need to do. U sub? Basic U sub. U is arctangent x. Derivative of it's there. Okay? So, but it's a definite integral, right? This is a definite integral. Do we have any issues at these values? We didn't check. At 0 and every number between 0 and 1, does it cause any problems in the denominator? No. How about up top? Arctan is defined everywhere. How do we know that arctangent is defined everywhere? You could look at the graph, but you could also think about the output or the range of the tangent function. What's the range of the tangent function? That's tangent, right? The range is everything. That means the domain of the inverse is everything, because the range and domain switch places when you do inverses. So we know that we can plug anything we want into arctan. We know the denominator is always good. So this is not an improper integral, right? This is not. It's a definite integral, but it's not improper. So u is arctan of x. Du is 1 over 1 plus x squared dx. And, well, that's just all right there, isn't it? So this integral is going to really become u du, right? U du. So the antiderivative of that is a half u squared plus c. So again, this is like my scratch work. I'm doing all this just to figure out what the antiderivative is. And now I go rewrite the integral. So that integral becomes equal to the antiderivative 1/2 arctangent of x, that quantity squared, evaluated at 0 and at 1. So we plug in 1 first, right? And then we plug in 0. So 1/2 arctangent of 1, that quantity squared, and then 1/2 arctangent of 0, and then that quantity squared. What is arctan of 1? Pi over 4. Arctangent of 1. So you should be asking yourself for this, you know, at what angle is my ratio of the y-coordinate to the x-coordinate 1? Right? Because tangent always spits out the ratio of y over x. So the only time you get a ratio of 1 is when the y and the x are the same. That only happens at pi over 4. And also in another quadrant, but arctan's only defined between negative pi over 2 and pi over 2. So this has to be pi over 4. So 1/2, what's pi over 4 squared? Don't forget to square it. Pi squared over 16, right? You're taking pi over 4 and you're squaring it. And then minus arctangent of 0. So what angle is your ratio of y divided by x 0? Only when your y is 0. And your y is only 0 at the angle 0. So this is 0. It's gone. So your answer should be pi squared over 32. Excuse me. Thank you. You already got me sick. Yes. Chapter review for the chapter 6 that I'm looking at starts on page 362. 362. Yeah. Okay, I'll give you a minute to look at that one.